Chapter 7, Techniques of Integration. In this chapter, we go through a number of techniques to calculate integrals, and the very first one here is integration by parts. This is basically a reversed product rule. In my opinion, this is a nice counterpart for integration by substitution that we went through in Calculus 1, because integration by substitution is also coming from the derivative computation rule, the chain rule. And if you look at the other integration techniques, those are just algebraic or something very different, as a matter of fact. These two, integration by substitution and integration by parts, are both coming from differentiation rules. Okay, here is our textbook's convention. The derivative of f times g is fg prime plus gf prime, and this kind of derivation follows. But personally, I'd much prefer my own conventions, so I'd rather go over to the mathematical notebook I created. And oh, by the way, I inserted a brief review on integration by substitution for a review purpose. That's left to the students. And then here is the integration by part and formulae. Okay, we begin with a product rule like this. The derivative of u times v is u prime v plus uv prime. The derivative of the first function times the second function plus the first function times the derivative of the second function. And then what do? We take the antiderivative. So the derivative of the antiderivative, the left-hand side, comes right back to the original, u times v. The right-hand side becomes the antiderivative, and then we can simply separate these indefinite integrals. And then what we have, we simply flip this first antiderivative to the other side, and then we end up with this. uv minus integral u prime v dx is integral of uv prime dx, Consequently, flipping them over, we get this very, very important formula, which we call the integration by part formula. Integral of u v prime dx is uv minus u prime v dx. If you're familiar with, or if you're more comfortable with differential computation, you can use the second formula too. Personally, I don't, but a lot of students like these. These two are the same because dv is nothing more than v prime dx, which I color-coded as blue. And then du is nothing more than u prime dx, which I color-coded in red. So the second formula and the first formula are actually identical. Okay, let's move on to example problems. And I like this one a little bit better, so I'd rather stick to... Oh, okay, I already moved it here. Okay, let me use that. Alright, how about this problem here? Integral of x e to the negative x dx. Big problem, which is u and which is v prime? The next problem, integral of x squared log of x dx. Which is u and which is v prime? Same question for problem C. T squared sine of 2t. Which is u and which is v prime? Well, that's not always an easy problem to answer, so let me give you a shortcut here. A hierarchy rule for integration by part, and this doesn't appear in our textbook or any textbook I have ever seen, to tell the truth. I just made it up. The reason is because this hierarchy rule doesn't always work. Works beautifully in a lot of situations, but in many situations it simply doesn't. So you cannot include this in print. But then again, I'm not writing a textbook here. This is just a lecture note, so I can get away with a lot of things. So I'll just use this hierarchy rule and get away with some exceptional cases. And if you find out in exceptional cases, please be warned. I already told you there are exceptions. Okay, in a lot of situations, however, and most of the cases where you're going to get exam problems, after all, I'm the one who is writing the exam problems, excuse me. In those cases, you can rely upon this hierarchy rule. So, we have a power function here, x to the k power, times exponential function. And in this hierarchy rule, exponential function has stronger tendency to become v prime. So this will be v prime, and then this will be u. How about part B? Power function and the logarithmic function, which has stronger tendency to become u and v prime. Log function will become u, and this will become v prime. And this is how it works. U is equal to x, okay, that's u, and v prime is e to the negative x, coming from that hierarchy rule. And then in order to apply this integration by part formula, you'll have to find out u prime and v. So take the derivative, so you get u prime. Take the antiderivative, you get v. Are we ready? Yes, we are ready. U times v, so cross multiply, x times negative e to the negative x, that's u times v. And then u v prime. No, excuse me, u prime v. So u prime v, so 1 times e to the negative x. And then after simplification, we get this integral of this exponential function, which is much easier integral than the original. So in the end, we have this. Let's go back to this original problem, and then you'll notice that we ended up doing 2 antiderivative computations. V prime to v, there goes one computation, and then this becoming that's the second antiderivative computations. Basically, the integration by part is allowing you to chop down one difficult antiderivative computation to 2 easier antiderivative computations, 1 and 2. And the derivative computation that show up in the middle, x is becoming, u is becoming u prime. That's much easier, so they don't count. Okay, alright, maybe 3 computations, 2 major, 1 minor computations. That's basically it. Let's do the same thing again, maybe many more times. Here it is. According to the hierarchy table, we have u equals log of x and v prime as x squared. And then we just apply the integration by part formula. U becomes u prime, 1 over x. V prime becomes v, so we did one antiderivative computation here. Not difficult at all, this is just a power rule. Put everything into this integration by part formula, uv minus u prime v. So uv minus u prime, which is 1 over x, times v. So after simplification, this is what we get, 1/3 x squared. This antiderivative computation is not difficult at all. This is just a power rule. So antiderivative number 2, that's much easier. Consequently, we have answer like this. Again, one difficult antiderivative is being decomposed into 2 easy antiderivatives. That's basically what happens here. How about the third problem? Hierarchy table says t squared is my u and v prime is sine function. Pretty clear from here. Sine has stronger tendency to become v prime, and power function has stronger tendency to become u. So let's apply the integration by parts, and here we go. U is t squared, v prime is sine of 2t, so let's calculate these antiderivative. It's here, and uv minus u prime v, after canceling out this negative and that original negative, we end up with this integral right over here. But then again, this is another difficult integral, so how do we handle this? Power function times a polynomial function times cosine function. That's again coming from this hierarchy rule, this part. So we use integration by part again for the second time. U is 1/2 t, v prime is cosine, and then just follow through the derivative and then the antiderivative. Put everything into this antiderivative formula for integration by part, uv minus integral of u prime v, and we get the final integral, and this is simple integral. All you have to do is to change sign to cosine, because the derivative of cosine is negative sign, and then by chain rule this 2 has to be divided again, so we have this 1/4. Basically reverse chain rule is being applied there, and we have the answer in the end. Integration by part twice, but both of them are just standard cases. How about the final problem here? Well, arctangent is gonna be u, and x will be, well, x to the first power. How about two power functions here, this one and that one? Which is u and which is v prime? Well, if you open up this cell, you're going to see the answer, but I want you to think before answering it. Alright, we have sufficient time left for next example. Let's go over to example problems where there are some hidden multiplications. And kind of like these, antiderivative of log function, antiderivative of arctangent function. Those do not look like integration by part problem because we do not have product here. But product is hidden. Actually, log of x is nothing more than 1 times log of x, as we see over here. And 1 is actually a power function here, x to the 0 power. So that is becoming v prime, and then antiderivative is v, and log of x is u, so the derivative is 1 over x. Putting everything into the integration by part formula, what do you get? uv minus integral of u prime v. After simplification, after simplification, this integral became that integral, and we have the final answer. So getting v prime equals to 1 and taking the antiderivative to get x looks like counterproductive because 1 is much simpler than x, but log of x was so complicated a function, but that is becoming 1 over x. You gain so much from there that v prime to v is just a small loss there. In any case, here's an example of hidden multiplication. The second example is also a hidden multiplication, so you'll have to do something similar about 1 times the arctangent and apply that hierarchy table, and we're gonna get an answer. Yes, u is arctangent, v prime is 1, and no cheating. I'm gonna ask you to try that on your own and use the answer key only as a last resort. Integration by part formula here, either this one or that one, they are extremely important, and I believe everybody has to memorize, and also everybody has to remember this derivation. The hierarchy rule, this hierarchy rule is not always right, but it works beautifully in a lot of situations. So I'd rather emphasize it, and I think everybody should remember this one. Some more advanced examples of integration by parts. I think I'll have to do this in the next segment of video. And even here, the examples where hierarchy rule fails will not appear. I mean, those examples are really rare. Okay.